Tonight's speaker is Krista West. Krista is a third-year student in the San Diego State University, University of California, Santa Barbara joint doctoral program. She uses pictures taken from high above the earth to learn more about the environment. Krista was a summer intern with the NASA Develop program and has worked with both the US Navy and Air Force as a civilian, taught as an instructor of geosciences at the US Air Force Academy, and worked closely with firefighters as a member of a startup called Intera. These last two opportunities in particular contributed to her decision to return to academia and pursue her PhD. In this work, she found knowledge gaps which she was confident could be filled by image data, the work she does now. Krista is also a member of the Climate Science Alliance's Connecting Wildlands and Communities Team FIRE. Krista aims to become a university professor and science translator and is passionate about performing research that helps emergency responders. We are so fortunate to have her here tonight to talk about this really vital topic. So welcome, Krista.
Thank you so much, Judy. I really appreciate this opportunity. Let's see, I'll make sure my slides are working. Okay, fantastic. So thank you very much to the San Diego Natural History Museum and the Climate Science Alliance for having me this evening. I'm so appreciative of the opportunity to talk with you all about projects with which I've been involved. And this evening, my goal is to address some of your burning questions about the effects of climate change on wildfire in California. And I will also share how I'm using satellite imagery from above to learn more. Just like all of you, I care about the environment and I want to learn more about climate change and natural disasters. I grew up in California, so I'm used to hearing about wildfires in the news. However, and I don't know about you, but I've started to notice an uptick in the number of fires, how much they burn, how long they burn, and definitely how many people they impact. And I got really interested in learning more about wildfires when I worked for that Colorado-based startup called Intera. They're a team of former firefighters, military veterans, and data and mapping geniuses who provide real-time information to firefighters. I loved working with Intera, and my passion for helping emergency responders and people living in areas that are at risk of being affected by wildfires just grew tenfold. However, I started finding knowledge gaps when it came to wildfire and use of map data and images, and that inspired me to return to school. So now I'm a San Diego State University, UC Santa Barbara Joint Doctoral Program student with the Departments of Geography. I'm really loving this chance to dive into the research world, and I hope that what I do will be useful for firefighters and communities at risk of fire. So I'm a geographer, and the work I do is within the field of remote sensing. So I think the easiest way to describe myself is as a remote sensing scientist. And what this means is that I use imagery and data captured by a variety of platforms. It could be hobby drones, planes, satellites, anything really to learn about our planet. And the key word here is remote, meaning I'm learning more about a place or an object without physically touching it. And I will dive deeper into remote sensing a little bit later in the talk. I've been fortunate to work with the Climate Science Alliance and Connecting Wildlands and Communities project teams for over 2 years now. And it has been with these teams' guidance that my research objectives were inspired. The Connecting Wildlands and Communities, or CWC project, is funded by the California Strategic Growth Council through the California Climate Investments Initiative. And it's a collaborative effort of the Institute for Ecological Monitoring and Management at San Diego State University and the Climate Science Alliance. Our big team is made up of smaller teams comprised of geographers, ecologists, biologists, hydrologists, planners, science educators, and we're focused on Southern California coastal shrubland ecoregions. And we're all about exploring how connected landscapes can support adaptation and resilience to climate change for both ecosystems and local communities. We're led by Drs. Megan Jennings, Rebecca Lewison, and Diane Foote, and I'm part of, surprise, Team FIRE, along with Dr. Doug Stowe, Aaron Conlisk, Chandler Ross, Emmanuel Story, and Alexandra Seifert. The Climate Science Alliance and Connecting Wildlands and Communities project teams are always working on amazing projects. So I definitely encourage you to follow both and get involved if you have time. So this evening, I'm sharing what I've learned about wildland fire in California. I'll teach a brief remote sensing 101 lesson, and then we'll discuss using imagery to learn about landscapes at risk of wildfire. If you're willing to share, however, I am curious to learn how wildfire has affected or impacted you in your lifetimes. Have you experienced a wildfire firsthand? Has something you've read or watched on the news been particularly impactful? Do you have a firefighter in your family? One of my earliest memories of wildfire is from a family drive through the Sierra Nevada foothills. I saw my first fire helicopter using a Bambi bucket to retrieve water from a small lake to drop on a fire. And now I have a bunch of firefighter friends, and that's part of what drives me to pursue fire-related research. I want to do what I can to help keep them safe. And if you would like to share a short memory in the Zoom chat box, I will circle back, and I would really love to read some of your stories. So when we address wildfire in California, it's important to define some key terms. And I'd also like to point out that throughout this discussion, I hope you'll keep in mind that wildfires are natural events that are necessary for many ecoregions, and not all fires are bad. Kind of like wolves and sharks, I feel like wildfire gets a really bad rap, despite being good for the environment. However, we do worry about fires when they negatively affect people and structures, when they occur too frequently in the same area, and particularly when they wipe out entire species of flora and fauna. So wildland fire, that's our first definition this evening. It's any non-structure fire other than prescribed fire that occurs in the wildland. So you might also be familiar with the terms wildfire, forest fire, vegetation fire, bushfire, brush fire, grass fire, depending on where you grew up, most likely. I use wildfire and wildland fire most frequently. Also, if you've heard the term complex fire, complex refers to two or more individual incidents located in the same general area, which are assigned to a single incident commander or unified command. A current example of a complex is the KNP complex that's currently burning in Sequoia National Park, where the Paradise and the Colony fires are located very close together. The wildland-urban interface, or WUI, refers to the line, area, or zone where structures and other human development meet or intermingle with undeveloped wildland or vegetation fuels. So examples of these types of wildland-urban areas are shown here, and my research focuses particularly on the interface and the intermix areas depicted in these example scenes on the top. So what factors are necessary for combustion and flame production? Well, we use the fire triangle as an instructional aid to answer that question. Removal of any of the three factors listed on each side would cause flame production to cease. So each of the sides include oxygen, and air must be at least 16% oxygen to support a fire. Keep in mind that the air around us is about 21% oxygen. Heat. To start burning, a material must reach its ignition temperature, usually hundreds of degrees. And the third side of this triangle is fuel. And fuel is anything that will burn, any combustible material that will feed a fire. Because we like triangles in the fire community, we also have the fire behavior triangle. So on one side of the behavior triangle, we have weather, like strong winds and low humidity. Another side is topography, mountain areas, canyons, or flat areas. And the third side, again, is fuel. And that's when we're thinking about plants that catch on fire and spread fire very easily. Something like eucalyptus, palm trees, and grasses, especially dry grasses, are flammable and what we call flashy fuels. Knowledge about variations in weather, topography, and fuels can help us gain a better understanding of how a wildland fire will act, whether it will burn slowly and stay small or burn quickly and at a very high intensity and temperature. While we're talking about fuels, I'd like to also talk about the grass fire cycle. It's an important component of the work I do. Invasive grasses contribute to a positive feedback loop called a grass fire cycle. And it occurs when grasses invade and as they dry out, become flashy fuel, which can lead to more frequent and intense fires that can spread rapidly and widely. The increase in grass cover causes a decline in native shrubs and trees, which allows for additional grass expansion and thereby increases the likelihood of future fire. Ultimately, these invasive grasses can completely replace the native vegetation. And data show that the risk associated with grass expansion has been exacerbated by climate change. And changing climates have led to warmer temperatures, an increase in extreme weather events, and drought conditions and drier vegetation. Finally, there's the fire regime. And this describes the patterns of fire occurrences, frequency, size, severity, and sometimes vegetation and fire effects as well in a given area or ecosystem. A fire regime is a generalization based on fire histories at individual sites. They can often be described as cycles because some parts of the histories usually get repeated, and the repetitions can be counted and measured, such as fire return interval. So now that those terms have been defined, we can return to fire science, specifically in California. Indigenous knowledge of fire on California landscapes has been around for at least 15,000 years and is passed down through oral history and ceremony, and the keepers of that knowledge are eager to put it to use. As early as the beginning of the 20th century, the U.S. Forest Service has worked in California to research how forest fires impacted landscapes in California, and even how climate is related to forest fire. The relationship between fire ecology and conservation for flora and fauna was studied, and places like Yosemite, Sequoia, and Kings Canyon National Parks are where some of those first studies began. We see a split, however, between the 20th and 21st century, between suppression and ecology. So in the 20th century, fire suppression asked, how do we stop or suppress destructive fire? We have a long history of suppression and disaster in California, and that has added to the number of lives lost, structures lost, and acreage burned. In the 21st century, we see a shift from suppression to ecology. And fire ecology asks, how is fire beneficial? And this is an extremely important question, and one for which I'm glad to see more emphasis being placed today. It has been shared by researchers like Dr. Krista Colden, an assistant professor at UC Merced, that many fire scientists first became interested and pursued science related to wildland fires because they were in California at the time of a large event, knew someone who was, saw it on the news, or were impacted somehow. And this has helped bring a lot of researchers into the world of fire science to help solve problems. So at this time, I would like to refer over to the chat box and read some of your responses. Thank you so much. I've been seeing them roll in. Maybe some of you are considering a career or second career in fire science. Let's see. Oh, so many fantastic ones. Well, we've got John Lee, who's the elected official with the Vista Fire Protection District. So thank you so much for participating in that. That's a hugely important job. C is impacted by wildfires. Family who was incarcerated and used for labor while getting paid $2 an hour. Oh, wow. You know, I attended a prescribed fire and I saw incarcerated firefighters, and it was incredible to see how hard they were working. And I hope that that program leads to something good. Thank you for sharing that story. Kathy Dunn's uncle spent his entire career in the U.S. Forest Service. In the first half of his career, he was involved in coordinating wildfire management in California and Colorado primarily. It's incredible. Oh, Nathan Kohlberg missed out on 6th grade camp. I believe it was around 2004. And Southern California had a serious wildland fire, and the city of San Diego was being covered in ash at the time. One of the first serious fires for which Nathan got to see the effects of up close. Yeah, I have a feeling there was certainly a large fire in 2003, but we've had 1 or 2 fires in Southern California, and we'll be discussing that later. Sorry about 6th grade camp, Nathan. Susan, during the 2003 fire, my daughter was staying at an animal rescue and called me early in the morning because of the encroaching fire. Susan drove her minivan there and saw the flames in the nearby hills. Oh my goodness, loaded the car with as many cats and crates as you could and drove them to safe location, plus one dog that you were fostering. Oh, thank you so much. We will talk about tips and tricks later for preparing for wildfire, and pets are such a big part of it. Kathy also had several friends burn out of their homes in the Witch Creek fire. Fortunately, they escaped with their lives. Oh, that's incredible. Ash, let's see, oops, I scrolled too much up. Ash was in San Diego for the 2003 fires that burned in the county. She was away for college during the 2007 fires and watched those progress over the news. Richard says, in August, I tried to take the Amtrak Coast Starlight train from LA to Portland. Ooh, lovely trip. However, Amtrak informed Richard that they had closed the track between Sacramento and Klamath Falls, Oregon, for 6 weeks. All they would confess to is the need for track maintenance and repair. Well, we do know from checking the news and the maps that there have been 1 or 2 fire incidents in that point. Anna from Climate Science Alliance says, growing up in San Diego, she's faced 2 evacuations from the Cedar Fire and Witch Creek Fire, which has certainly made her more mindful of wildfire's role in the environment, how she can best prepare for an unexpected evacuation, and the incredible transformations that can occur after a wildfire. You highlighted all of the amazing points. Thank you so much. Z, non-native plants being planted by firefighters in the past. I'm not going to touch on that, but I will definitely talk about non-native plants. Stephanie says, oh, student at UCSB, woo, during the Thomas Fire in 2017. Oh, yep, okay. Due to the air quality final exams were postponed and you were sent home. Congratulations on the postponement of final exams. Hopefully, sorry that you were sent home. We will be talking about the Thomas Fire this evening. That was an extreme event. Karen says Scripps Fire lived in Mission Valley where you're surrounded by 3 fires. That is terrifying, right? Because evacuation routes are certainly something that you want to be aware of, but sometimes that data isn't always readily available. And it's very scary if you don't know where is safe to go, particularly when you're consumed by smoke. Steve says, when I was a teenager living in the LA area, a large fire burned for days, pushed by Santa Ana winds, that eventually reached our house. Oh no. Although the entire area's vegetation was completely burned, somehow our house didn't burn. Oh, thank goodness. Later, I spent a little time as a wildland firefighter in Arizona. Oh, thank you so much, Steve. Dan says, hoping those studying the fire regime are looking at how firefighters are affecting the size and severity of these fires. Certainly. John was evacuated twice, once sustained roof damage from a fire, and firefighters saved their home. Oh, thank goodness, John. Keith in the early 70s evacuated from Angeles National Forest. Oh my goodness. National Forest due to wildfire. Oh, and then Tubbs in 2017. Yikes. Let's see, Kyle. Oh, Kyle lost place of work in the 2003 Cedar Fire. And then Dan mentioned thoughts about unintended consequences of some of the environmental laws affecting firefighters' abilities to control burns and how this affects my studies. That may be out of the purview of today's talk, but I would be happy to follow up with you. I will provide my email address. Yep, Alyssa made a great comment to Z, and I will just read 2 more and then we will hop back into the talk because I have so much I want to share with you. Oh no, Susan had a misinformed landscaper, would only use native grasses and no others because they were fire bombs. Whew. Yeah, but with the drought, you know, a grass is a grass at some point. And then Dan says, Dan was an aerial firefighter involved in many of the 2003 to 2015 fires spanning the state of California. Much to learn here. Dan, I have very much to learn from you. So thank you all so much for sharing your stories. And I will hop back over to the presentation, but seriously, thank you so much. Okay, so these next maps may resonate with some of you, particularly those of you who shared your stories. Here are wildfire polygons that represent areas that burned before 1950. And we see that large parts of the state, particularly the southern coastal shrubland ecoregions and the Sierras, where we have a lot of evergreen trees and forests, those have burned historically. But when we compare the last few decades, and I will flip back and forth, we see two things, really. Many of the same places have burned, and also we see much larger areas that have been affected by wildland fire. So again, please remember a quote that I love from Dr. Michael Gollner from UC Berkeley: "Fires are natural inhabitants of the landscape, and not all fires are bad." Some of those landscapes, some of which are very large areas in our beautiful state, do require a fire every so often, but some fires are bad. And what makes a fire disaster? Home and structure destruction, certainly. Lives lost, 100%. Affected ecosystems and ecosystem services, referring to clean air, clean water, and recreational opportunities. All of those things. And it's very difficult to define, but we have been seeing a crossing of thresholds in California, particularly in the last 20 to 30 years. CAL FIRE data communicate the top 20 most destructive, deadliest, and also largest wildfires in California. And I realize that this is a bit of an eye chart, and I will scroll through them quickly, but I can absolutely make those statistics available. These data on these tables are from the last 2 days. Any incidents that are written in red font are indicating that they don't have final data yet, just because those fires have not yet been fully contained. But if we take the data from the list of the largest fires or area burned, we can plot it against the number of fires, and we'll end up with a graph like the one we see here on the left. We can also look at the cost of suppression activities over time over here on the right. And these data communicate values collected from between 1985 and 2019 or 2020 in the United States. What we're seeing is that since 1985, the number of fires per year is going down, the blue, but the black line, the fire size is going up. And about 3% of the fires are responsible for most of this area burned. Now look at the trend for just California in those same time periods. So during extreme weather events, high winds, drought, dry fuel, dry soil, fires grow very large, and the cost of fire suppression is increasing over time. We're starting to move to a new fire regime in California, and California suppression costs follow a similar trend of that for the entire US. Up, right? They're definitely both increasing. So that leads us to a question. What could the drivers of these changes be? What do you think might be affecting these trends in wildland fires in California? What's happening and what will happen to fire regimes? Well, it seems obvious that as temperatures rise with climate change, there will be more fires that burn more land. But it has been found that predicting future fire regimes is not rocket science. It is far more complicated than that. And this is a quote from Doctors John Keeley and Alexandra Seifert from a research brief they prepared for a resource managers meeting for the 2016 California Fire Science Consortium. And I like to share it to point out that this is a tough problem. There's not a single solution. There's no one-size-fits-all solution. And there are a lot of factors to consider. Returning to our question about possible drivers of changes, we observe 3 big drivers that are discussed most frequently in the literature. The first is a history of fire suppression. We know that Spanish colonizers suppressed indigenous fire use, and then federal suppression began in the early 20th century. Suppression has led to a massive buildup of brush and fuels. The second point that we like to think about is expansion of the wildland-urban interface. More lives and structures are lost because they are located on that edge, that interface edge between city and wildland spaces. And due to the density of humans and vulnerability of structures, we see increased fire risk. And certainly as population goes up and people spread out to the gorgeous wildland areas, we see a lot more people affected. And then the third, which is why you're all here, climate change. The incidence of drought and presence of invasive species like non-native or invasive grasses or pine beetles, which have contributed certainly to vegetation mortality, has played a role. as has extreme fire weather. We've seen high frequency and high magnitude weather events, firenadoes, pyrocumulonimbus clouds, that have led to some of the deadliest incidents, and the weather is associated with anthropogenic or human-caused climate change. A large proportion of what we have seen burned in the last 15 to 20 years has been strongly associated with anthropogenic climate change. And results from doctors Abatsoglu and Williams showed that about 4 million additional hectares of fire went essentially above and beyond what would have been expected without human-induced climate change. If you do some of those conversions in your head, 4 million hectares is just under 10 million acres, or just over 15,000 square miles. From a study produced by Dr. Westerling for California's 4th climate change assessment, when we look at monoprojections for future in terms of future projected area burn based on the Intergovernmental Panel on Climate Changes, or IPCC's global climate model outputs, we see these outputs produced by Dr. Westerling shown here. And this dashed line added by Dr. Krista Colton shows area burned as of September 2020, so a year ago, just under 1 million hectares, or 2.5 million acres, or almost 4,000 square miles. And that was burned for the year, which puts us ahead by 20 to 30 years of what model projections showed for some of the extreme fire years. What are these data telling us? Basically, there is evidence that climate change, particularly anthropogenic or human-caused climate change, is playing a big part in California's wildfire situation. What needs to happen? First, there's a need for interdisciplinary work, research, development, and education. To have fire resilient and fire adapted landscapes, we need to address management of landscapes. We need to reduce barriers to cultural, political, and economic implementation. Human behavior, mitigation, preparation, planning, notifications, and evacuation options must all be addressed. They're extremely important. And public health implications such as smoke, air quality, and water quality need to be better understood as well. We also need to ensure that everyone understands just how many disciplines need to be involved in wildfire management. I've highlighted a few here, but since I'm a remote sensing scientist, I would like to now talk with you about how imaging technologies like remote sensing can be used to learn more about wildland fire and climate change. So what is remote sensing? I touched on it briefly in the beginning, but defined, remote sensing is the art and science of obtaining information about an object without being in direct physical contact with that object. It can be used to measure and monitor important biophysical characteristics and human activities on Earth or other planets like Mars. So remote sensing can be used to solve real-world problems. It can be applied to physical geography, biogeography, geology, hydrology, urban planning, agriculture, forestry, marine science, and much more. If you've ever used a tool like Google Earth or Google Maps to look at your house, congratulations, you're already a remote sensor. For much of the work I do, I use imagery acquired by satellites in space. Every day, all the time, we have satellites that are orbiting Earth and collecting data. Some are equipped with special cameras or sensors, and I use data from those sensors. What I love about these sensors is that they can see beyond what you and I can see with our own eyes. Our eyes have 2 types of color receptors, rods and cones. Rods are what allow us to see brightness in shades of gray. For example, rods are what help us see better at night. The cones in our eyes are what help us see color in the daytime, and we have 3 types of cones that help us see: red, green, and blue light. And the mixture, this is important, of red, green, and blue is what we call visible light and what we call true color imagery when we look at image data. You'll hear me mention visible and true color imagery 1 or 2 more times at least. So to demonstrate, here's what we'd see when you and I look at Mission Trails Regional Park grassland. And just for fun, here's what your dog or cat would see when they look at the same open grassy space. They have more rods, but fewer cones in their eyes. So they can't see color as well as we do, but they do see better at night. Speaking of lighting, as the sun sets, I feel like I need to turn on my lamp. So I'm gonna reach down and hopefully it won't blast you all with brightness. Stand by for just a second. Oh, wow. Well, it's quite bright, but hopefully it's a little better. Okay, so in addition to seeing visible light, the sensors I use can detect other types of light and energy within the electromagnetic spectrum. The sun provides a continuous spectrum of energy, all the way from teeny tiny gamma rays to very large radio waves. And we see visible light, red, green, and blue, true color, but the sun sends us all these other wavelengths that we cannot see with our eyes. They hit the ground, some are absorbed, others transmitted, and others are reflected. Everything on the ground has its own unique spectral signature or spectrum, and that is what gets captured by the sensors as they move overhead. Here's the electromagnetic spectrum. As I mentioned, our eyes see visible light, this very small portion of the full spectrum. For work related to climate change, particularly when focusing on the effects of climate change on vegetation, I focus on the infrared part of the electromagnetic spectrum. In order to create a data output that answers my research questions, I work with a combination of 3 parts of the electromagnetic spectrum, and I can pick and choose how those parts are ordered. And those parts are called bands, and this process is referred to as band manipulation or manipulating bands. Each band represents a small portion or segment of the electromagnetic spectrum, and I decide which part to highlight based on my research objective. I know this might be a bit confusing if you haven't learned about remote sensing before, so one way to think about it is to imagine a piano keyboard. We have all of the keys on the keyboard, and if we choose just 3 keys and play them at once, we hear a sound. With remote sensing, we choose 3 bands and we see a picture. And depending on our sensor, we could have anywhere from tens to hundreds of bands from which to choose. And if we want to see a picture, as we would with our eyes, again, we choose the 3 bands that output a visible or true color image: red, green, and blue. Selection of red, green, and blue outputs a visible or true color image. As if you were looking at the landscape while flying over the Thomas Fire in December 2017, you would see brown, bumpy mountains. You'd see some agricultural fields with green vegetation, some smaller urban areas that look white or bluish because of asphalt concrete rooftops, and then the smooth blue ocean down here in the southwest corner of this image. This image, by the way, was acquired by a satellite sensor called Sentinel-2, which is operated by the European Space Agency. If you want to focus on vegetation in your image, however, a common band combination is near-infrared red and green. So now, healthy plants appear to be red, and that is because we are incorporating this infrared band. The bright red is indicating very healthy and very well irrigated plants, such as those in this agricultural area. The darker red is still showing vegetation, but it's more a wildland landscape where the vegetation relies on rainfall as opposed to regular irrigation. And these bands are from a single image. All of these bands representing small parts of the electromagnetic spectrum are captured by a sensor at the same time. So we can use a single data file and get all of this information. Based on this ability, I hope I've at least started to convince you that there are applications for remote sensing to learn about landscapes and vegetation affected by climate change. What about remote sensing of landscapes at risk of wildland fire? We can also use remote sensing to monitor areas before, during, and after a wildland fire incident. When we look at vegetation with the near-infrared band, we saw bright red plants, and we could learn about areas with healthy versus dry or senesced or dead plants, which, as you know, is perfect fuel for a fire. So what can we see as the fire is burning? Using the shortwave infrared and near-infrared bands, we can better see the area that has burned, called the burn scar, and even the actively burning fire front. Again, this is the exact same image that I've been showing you as before, but with these bands, we can see through the smoke better than we could using the other bands. Now, healthy, irrigated vegetation is bright blue. Wildland vegetation is darker blue and turquoise. And if we zoom in on this spot, we'll see that the burn scar is a sort of goldenrod brown shade. And look at what we have here. The active fire is yellow and orange, and you can see exactly where that burning fire front is. We can also work with many images and monitor location over a longer time period. So here are images captured by a bunch of PlanetScope sensors, and PlanetScopes are operated by a company called Planet. And with so many of their sensors, they have hundreds, data users can acquire images over the same geographic area almost every day. And so when the satellites are in orbit, they capture these long swaths of data imagery. And if there's a spot where you don't see any imagery, that means it wasn't collected there that day. So as a remote sensing scientist, I gather all of the data that does exist for a time period and I stitch it together, kind of like a puzzle. And so as we slowly progress through each day's image collection, you can see the date traveling along down here. You'll start seeing the smoke from the Thomas Fire, which burned from December 4th, 2017 through January 12th, 2018. And since we have multiple images, we can watch the progression of the fire and we can gather evidence about the landscape. For example, smoke that is more white or blue is generally from moist and healthy vegetation that is burning, compared to smoke that is more brown or yellow, which indicates that the vegetation that's burning is dry, senesced or dead, possibly because of the season or due to drought conditions. So that was visible or true color imagery collected from space. But what about data that use the infrared band and are acquired by an airborne platform like an airplane? So here is a video captured by the Colorado Division of Fire Prevention and Control's multi-mission aircraft, also over the Thomas Fire. The video switches between the visible or true color and infrared output. So when you see the black and white, that's the infrared, and the brighter or wider the pixel is indicating a hotter spot on the ground. If it's a dark pixel, then that means there's a lower temperature on the ground. So again, very bright areas up here means that's closer to where the fire is burning, and the dark areas are indicating a cooler spot. So we call the grass fire cycle. Data have indicated that these flammable grasses have expanded over time, and this may pose problems for fire management and biodiversity-focused teams. For my dissertation, I'm focusing on research objectives raised by the Climate Science Alliance Connecting Wildlands and Communities project. My research objectives are to use remotely sensed data to locate and quantify areas where natural coastal shrubland ecoregions have experienced a decrease in shrubs and an increase in Southern California grasses, both native or non-native. And similar to the images I was showing before, I'm manipulating those band combinations and applying different remote sensing techniques to learn more about the landscape. And I'm looking at data collected between 1984 and present. Out of the entire CWC study area, ranging from Santa Barbara down to San Diego County, outlined here in yellow, I began by focusing on a very small area of interest and testing out different methods. So my study area is Mission Trails Regional Park here in San Diego, and I started by learning more about that area and different ways to observe change in land cover type using a tool called the Rangeland Analysis Platform. So here is Mission Trails Regional Park through time using data from that Rangeland Analysis Platform. I'm looking at shrubs on top and grasses on the bottom. The bluer colors indicate a low percentage of that cover type at that time period, whereas red would indicate a very high value at that time. So just for reference, this is a good one. You can see this dark blue spot right here in the shrub row is the Mission Trails Regional Park grassland, whereas up here, there is Coles Mountain, and so more shrubs, right? So you might wonder why I don't just look at data from the beginning of the time period and the end, just 1986 or just 2019. And since there's more than one land cover type, it's very heterogeneous, even in a small area like Mission Trails Regional Park, I need to observe changes to the landscape through time and can't just assume that we'll learn everything we need to know from the first and last dates. For example, I have a feeling many of you will know that there was in fact a particular event that occurred right here in 2003 that would have caused a decrease in shrubs, the blue, and an increase in grasses by the time these data were collected in 2005. It was the cedar fire. So to map grasses, I'm using remote sensing to develop, apply, and validate invasive grass cover mapping and change monitoring approaches based on image data acquired since 1984. I'm using data from the Landsat sensors, and Landsat is a program operated by NASA and the US Geological Survey, and it has been running since 1972, which is the earliest out of any civilian space remote sensing resource. And after stitching images together, I can crop them to the CWC study area, and then I can focus on different wildland areas like Mission Trails Regional Park. And because I can go all the way back to 1984, this means I can look at areas that have experienced grass cover expansion over time. And as I work with the CWC to analyze grass expansion in SoCal, we aim to address the consequences of grasses invading natural shrubland ecoregions, how their presence affects fire risk, and the role this expansion may play on both the local landscape and the fire regime. So here you see a product that communicates absolute change in time in grass cover between the mid-1980s and present day. And areas that have experienced an increase or expansion in grass cover are more red. And just to get a better idea, here are some zoomed in views of just a few locations. So by mapping and monitoring invasive grasses, we're creating products that will help our stakeholders assess past changes to the landscape, the current state, and potentially, hopefully, to forecast future changes. And then our stakeholders will be armed with the knowledge they need to make recommendations to pursue restoration strategies in wildlands or mitigation activities for communities before the start of the next wildfire season. I'm also looking at seasonal data and evaluating my results for San Diego County. And here are some photos I've taken in or near Mission Trails Regional Park in March and September. And not only are these seasonal differences important in terms of fire risk and ecology, but they're just also really cool to study when it comes to remote sensing techniques, because you can see just how different they are in visible imagery. So it's pretty interesting to look at it with the infrared imagery as well. Many people ask me what they can do to prepare for wildfire, and I recommend you start by following the experts. I'm talking about CAL FIRE, San Diego City, and county firefighters. The most important step you can take right now is to ensure you're wildfire ready, and organizations like CAL FIRE provide those resources to do so. Here are some additional resources and links that I recommend. Good books. In fact, Dr. Doug Stowe is using this Fire on Earth textbook for his SDSU Geography World on Fire class this semester. There's also some really excellent seminars organized by UC Berkeley and UC Merced experts. Nat Talks, particularly by Dr. Megan Jennings from last October. And all of these other organizations that I have listed here are just incredible resources. This is not an exhaustive list, but if you're wondering where to start, this is not a bad place. And if you specifically want to help with my research, I would really help if you would all log wild grasses, both native and non-native, around San Diego County in iNaturalist, so that I can use your inputs as reference and validation data. So thinking back to our earliest question, is climate change to blame for California wildfires? What do you think? It's certainly a complicated problem, but the data do support a changing climate due to anthropogenic causes, and wildfire events are becoming more extreme and negatively affecting and impacting more people and landscapes. I'm so thankful to be able to talk with people like you about this very hot topic. And I'm optimistic that the more we work together, the sooner we'll be able to determine the most appropriate mitigation and preparation steps to keep everyone safe in every type of environment. And I hope you'll keep in touch with me over the next couple of years as I continue this research and complete my PhD program. Thank you very much for the opportunity to speak with you all this evening. If you have more questions or would like to reach out and say hi, here are some ways to get in touch with me. And at this time, I would be very happy to take your questions.